Welcome to this recording from the Further Math Support Programme for Edexcel Statistics 2. In this recording we're going to be looking at the binomial and the Poisson distributions. So, things you need to be able to do. You need to be able to recognise and comment on whether a binomial or Poisson is a suitable model. It's very important that you appreciate that these are discrete models, and I'll talk about that in a bit more detail later. You need to be able to calculate probabilities by either using the tables, which are incredibly convenient, or the formulae, which are very, very useful when you can't use the tables. You also need to be able to find the mean and variance of binomials and Poissons, and most of this is actually in the formula booklet, so it's not too bad. Now, a lot of students find this topic particularly straightforward, but lose a lot of marks, and the reason is, as I said, the binomial and Poisson are discrete distributions, and students are used to using the normal distribution from an S1. So when we're using the tables to calculate probabilities, we just need to be a little bit careful when we do that. So, question from January 2010. A manufacturer supplies DVD players to retailers in batches of 20. It has 5% of the players returned because they are faulty. So a typical question that they can ask is this: write down a suitable model for the distribution of the number of faulty DVD players in a batch. Now this is discrete because we're talking about the number of things which are faulty, so that's how we know it's discrete. But we have to choose between the binomial or the Poisson in this particular case. So the conditions for a binomial are as follows. Do we have a fixed number of trials? And the answer is yes, we're doing it 20 times, and that's usually a dead giveaway. Do we have a fixed probability of success? And the answer is yes. So that was 20. We've got 5%. They have to be independent as well. And we have to sort of make sure that we are happy to make that assumption, which we are. Now, it says write down a suitable model. What I prefer students to write is to define their variable. So let x be the number of faulty DVD players. Sometimes on mark schemes this is important, sometimes it isn't, but if you're always going to write it, then you're not going to lose marks there, are we? So then we need to define it. So x can be modelled binomially with n as being 20 and p as being 0.05. So in this particular case you get 2 marks. They're both B marks, so you get 1 for telling me that it's binomial, and you get your second mark for actually giving me the correct values that the binomial is taking. The question then continues. We're then asked to find the probability that a batch contains no faulty DVD players. So because I've already defined what x is, I can actually use that. So no faulty players is going to be the probability that x equals 0. Now, in this particular case, I'm going to use the formula to do this. You could use the table, but I think it's good practice to look at. The formula states this: the probability of getting a specific value is equal to n combination x, p to the power of x, q to the power of n minus x. So in this particular case we've got 20, choose 0, 0.05 to the power of 0, 0.95 to the power of 20. And if we calculate that, we're going to get 0.3585, which you can see nicely corresponds to what we've got in the table here. So that's good. So you get 2 marks. One is for either using the table correctly or using the formula correctly, and then of course your accuracy mark is for actually getting the right answer. So more than 4 faulty DVDs. So this is where people go wrong. So I'm interested in 5 and above effectively, so I am not interested in 4 and below. Now, making sure that we're using this symbol here enables us to use the formula, the tables correctly. So this is going to now be 1 minus 0.9974 directly from the tables, which is going to give me 0.0026. So again, you get 2 marks here, 1 for basically using the table, and 1 mark for getting the correct answer. When we're using the table here, it's the 1 minus that we're interested in to get your method mark actually in this particular case. We're then asked to find the mean and the variance. Now we're told that for a binomial distribution that the expected value, which is in effect the mean, is equal to n times p, and the variance of x, which is sigma squared, will be n times p times q. Now notice np can usually always have been found, and that's just a useful trick to bear in mind. So here n was 20, p is 0.05, which gives me a value of 1. So I can now state that this is np, which is 1, times by q, which gives me a variance of 0.95. So it's 2 marks, 1 mark for getting each one correct. These are given to you in the formula sheet, so you don't get much credit for those. It's just getting the right answer that they're interested in here. Okay, so looking at a different question. A robot is programmed to build cars on a production line. The robot breaks down at a random rate of 1 every 20 hours. Now, this is an absolute dead giveaway that we're dealing with a Poisson distribution here. For it to be Poisson, we need a constant rate, and it also needs to be singly in time and independent as well. But in this case, looking for a constant rate is the key thing. So we're asked to find the probability that it will work continuously for 5 hours. Now, with a Poisson, the time frame is absolutely critical. So we work continuously for 5 hours without a breakdown. So again, define. So let x be the number of breakdowns in 5 hours. That's really important. Okay, so we expect 1 every 20 hours. So in this particular case, we are going to expect 0.25 in a 5-hour period. That's just achieved by doing 1 divided by 4. Okay, because we want to get it down to 20 hours. So now we can answer the question. So find the probability that it will work continuously for 5 hours without a breakdown. So that would mean the probability of x equaling 0. So to do this, I'm going to be using the formula. The reason is cumulative tables only have your parameter in values of 0.5. 0.25 is not a multiple of 0.5, so we're kind of using a formula here. And a reminder, the formula is the probability of x equaling a specific value is going to equal e to the minus lambda times by lambda to the power of x over x factorial. So in this particular case, we've got e to the minus 0.25 times by 0.25 to the power of 0, which is 1, divided by 0 factorial, which again is defined as being 1. So we're left with e to the minus 0.25. Now we've got 2 marks so far. We've got 1 mark for stating the formula and using it correctly. We then get a mark for defining the distribution in the first place, and then we get 1 mark, your accuracy mark, for calculating this out at the end. And again, 4 sig figs would be appropriate here. So now we're asked to find the probability that in an 8-hour period. So we've got to just think about this. We're told that there's 1 every 20 hours. So therefore there is 1 out of 20 every hour. So there is going to be 8 out of 20 every 8 hours. So we need to be very, very aware of this every single time. And we were looking for the probability that the robot will break down at least once. So now, again, define. So let y be number of breakdowns. And this time, as I say, we're looking in an 8-hour period. So breakdowns in 8 hours. So this time, y can be modelled as a Poisson distribution. 8 over 20 is 0.4 as a decimal, which again we can't use the tables for, we have to use the formula. So the robot will break down at least once. Now the probability is kind of pointing the wrong way, so 1 or more is the same as saying that you don't want 0. So again, using the formula that we had before, just going to put it into context again, so it's e to the minus lambda times by lambda to the y over y factorial now. So that's going to give me 1 minus e to the minus 0.4. And again, in this case, lambda to the 0 and 0 factorial are just going to give me values of 1. So we've now got 2 marks for this question. You've got 1 mark for defining. You've got another mark for getting to this point. And then it's just calculating it from here. So we work that out, 7032. And that's going to give me to 4 decimal places 0.3297. And that's your 3rd mark. Again, find the probability that in an 8-hour period there are exactly 2 breakdowns. So this is going to be now the probability that y is equal to 2. So this is quite nice. This is going to be e to the power of minus 0.4 times by 0.4 squared divided by 2 factorial. So you get 1 mark for applying the formula correctly, and then of course you're going to get your second mark, your accuracy mark, for getting the correct answer. And again, don't forget the general rubric is 3 significant figures or better, okay, unless stated otherwise. So in a particular 8-hour period the robot broke down twice. Write down the probability that the robot will break down in the following 8-hour period, and we're asked to give a reason for your answer. Now it's going to be 0.3297. Okay, and the reason is this. This is the probability that it's going to break down at least once. Now, one of the key things about a Poisson distribution is that time zones, so the periods of time that we're dealing with, are independent. So we know that each 8-hour period is independent. Okay, so it doesn't matter what's come before. So the probability that the robot will break down is independent of what's happened previously in a previous 8-hour period. So that's why the answer there is exactly the same as it would be in part B. Now, of course, if you got part B incorrect, as long as this was correct, you would still pick up potentially both of the marks for this. Okay, so Poisson events are independent is fundamentally what we're looking for here. Okay, so another question, January 2011, question 6. Cars arrive at a motorway toll booth at an average rate of 150 per hour. So again, we can see that we're dealing with some form of Poisson distribution here. So when it says suggest a suitable model, then that's what we're going to have. So we're told what x is, so we don't really need to define it, but it's always useful to anyway. So let x be number of cars arriving. Doesn't take long, but it's just worth always just making sure that it's clear. Okay, so we've just established that it's going to be Poisson, so x is Poisson, and per minute we're looking for now. So if it's per hour, we need to divide it by 60 to work out per minute. So you've just got to be really, really, really careful with this. We're then asked to state the assumptions. Now there are 3. Okay, and you've got to be very, very careful with the language. The whole question is about cars arriving, so that is key. So cars arrive, need that statement. So cars arrive at the booth independently. So the fact that one car arrives is independent of another one. Cars arrive singly. In other words, you can't have 2 cars appearing at the same time. And the rate of arrival is constant. Okay, that's a key aspect of the Poisson. Now, there are 3 here. Now, it's worth 2 marks. What you're allowed to do on Edexcel is to write all 3, and we will mark the best 2 of the 3 that we see for the marks. Okay, so my advice is always write the 3 out. Okay, this is quite unique for Edexcel, to be honest. So it might probably not work with any other subjects, but certainly for this, then we can get away with that. So using this model, we want to find the probability that in any given minute, so there's a reminder, no cars arrive and more than 3. Now, whenever you see that your Poisson variable is a multiple of 0.5, this is good news because it means you can use the Poisson tables. So for part I, no cars arrive. So this is the probability that x is equal to 0. And that can just be read off the table. So the probability of x equaling 0 when parameter is 2.5 is just simply going to be 0.0821. So that's quite nice. More than 3 cars arrive. So again, that's the probability of x being greater than 3. That's pointing the wrong way to use the tables. So I want 4 or more, which means I don't want 3 or below. Bit of advice is to write some numbers out. So 0, 1, 2, 3, 4, 5, 6, 7. And I am interested in these numbers, so I don't want these. Okay, so that's where that comes from. It's always a good idea to do things like that. Then we're just looking this up in the table. And if we do that, we get 7576, which we can then calculate really quite quickly as 0.2424. Again, don't cut short the numbers when you're using the tables. Use the full four digits in this particular case. So you get 3 marks here. For part I, you get 1 mark, well, basically just for reading out of the table or using the formula. You're more than welcome to do that. And then for part 2, it's 1 mark for the 1 minus probability being correct. And then of course you get your accuracy mark for the end bit. So cars arrive, same question, in any given 4-minute period. Okay, so we're now talking about a different distribution. So we should tell me what y is, but now we're dealing with 4 minutes. Your variable now is going to be 10. And we're looking for a value of m such that the probability of exceeding it is equal to 0.0487. Now these questions are designed in such a way that it is convenient to use the tables. So we need to realize that the probability of, I've called it y in this case. I mean, it doesn't really make any difference as long as you're happy with what you're dealing with. So the probability of y being greater than m is equal to 1 minus the probability of y being less than and equal to m. Okay, so if we just look at that, we need to realize that I can get this from a table. So the probability of y being less than or equal to m is equal to 1 minus the probability of y being greater than m, which is 1 minus 0.0487, which is going to give me a value of 0.9513. So for Poisson 10, we can see we've got 0.9513, so that indicates ever so nicely for me that m must equal 15. So this is worth 3 marks. Okay, so you're going to get 1 mark for recognizing that we're now dealing with a Poisson 10. You're going to get another mark for effectively rearranging this so that you can use the tables, and then you get your accuracy mark again at the end for getting the correct answer. Okay, and anything other than 15 is not going to give you any marks for that whatsoever. So I hope you found that useful. I recommend that you go through all of the past questions and make sure that you can answer all of these binomial Poisson questions. A lot of the time you're then asked to do approximations, or you're asked to do hypothesis tests as well, which are obviously cleared in later sessions.